Okay, good morning or good afternoon. So today we're going to continue with talking about linear algebra. I've kind of decided to lump all of our linear algebra together. Sometimes I spread it through the course. Sometimes I do what I'm doing this year. If you're wondering why there's this huge chunk of weird linear algebra in the middle of the course, it's because that's how I've decided to organize it this year. We always cover it every year. It's just that it's coming at you all at once. Okay, consistent with what I've said in the past, we're not really covering anything in linear algebra that you don't know, just kind of talking about it differently. And last time we saw a standard kind of a topic, the change of basis formula, but talked about that differently. We talked about dual spaces, and dual spaces are simply particular kinds of linear maps, so namely linear maps from a vector space into the scalar field. In this case, our scalar field is always the real numbers. And last time what we saw was that, so let me just sort of remind you where we were last time. Let V be a finite dimensional real vector space with a basis. So last time we defined a basis, which I, sort of either elegantly or confusingly, depending on your take, denoted by the same letters as I use for the basis here, but with superscripts to index the dual basis vectors as compared to subscripts used to index the basis vectors. Okay, so we defined a basis for the dual. So let me make that look more like a V than a U. And so remember that the dual space is, for us, it's simply the set of linear mappings from B into R. Okay, and the definition of the jth one of these basis vectors is that EJ, acting on a vector V, and a vector V we're going to expand in its basis. Okay, and the dual vector E super J serves the role of grabbing out the jth component of the vector in the basis E. Okay, so it's a known kind of a thing, and this is called, of course, the dual basis. Okay. All right. So let's look at this via an example. Okay, and the example is meant to be familiar, and so make the idea of a dual space and a dual basis seem familiar to you, but it runs the risk of oversimplifying the idea. So the example's good, but don't try to take more away from it than it's actually telling you. Okay, and I'll point out exactly where the possible pitfalls in interpretation are. Okay, and of course the vector space is going to be everybody's favorite n-dimensional real vector space, Rn. Okay, and then we take the standard basis. Okay, and I guess we know what that is. So E1 is a vector in Rn, and it's the vector which has a 1 and in the first place, and all the rest of them zeros. and E2. Okay, so we know what the standard basis is. Okay, so the question is, what's the dual basis to the standard basis? Okay, well, first, because we have a very simple vector space here, Rn, we're going to represent linear mappings from Rn into R, i.e. elements of Rn dual. We're going to represent those in a very concrete way, okay? Okay, so now we're just, the dual space is simply the set of linear mappings from Rn into R. Okay, and so we note, or let me just say it this way, we naturally identify, let's say, alpha in Rn star. Okay, and again, that's the set of linear maps from Rn into R. Okay, and so anytime we have linear mappings between Euclidean spaces, there's naturally associated to those things a matrix. Okay, and you know, one way to think about that matrix is that it's the matrix associated. Let me just, I'll write something down here, and then I'm going to erase it because I don't care about it that much. But just to remind you, if you have a linear mapping from Rn to Rm, let's say, slightly more general, then we can think of these as being matrices, and the matrices have what size? Well, they will have their maps into Rm, and so they will have m rows and n columns. So it will be Rm by n. Okay, and so we're going to use this here, and we're going to write elements of Rn dual as 1 by n matrices. Okay. All right. Okay, so what are these matrices? What are the standard dual vectors? Or sorry, what's the dual basis to the standard basis? Thinking of these as being 1 by n matrices. Well, you know, one way to do this is to try to figure it out. The other way to do it is to do the obvious thing and then check whether it's correct. And that's what I'm going to do. So I'm going to write E super 1. Okay. So this is to be distinguished from E sub 1. So and so I'll say more about this, about how to think about what this is. I write this as a vector in Rn, and as such, it's, you know, an n-tuple of numbers. Okay, E super 1, I'm not going to think of it as an n-tuple of numbers. It's going to certainly be represented by n numbers, but it's going to be a 1 by n matrix, and that 1 by n matrix is 1, 0, 0. Okay, and then E2 is 0, 1, 0, down to En, which is 0, 0, 1. Okay, so these are now matrices. Okay. All right, so make sure that you understand the difference between that and that. Okay, this is an element of Rn. This is a 1 by n matrix. Okay. Now, so let's maybe try. So there's another way that you represent vectors in Rn. You might want to write them as columns, right? As a column vector. You know, by the very definition, a vector in Rn looks like that. Okay, and that's the only thing it could possibly look like is that. It's not a column vector. However, there's a natural way of taking every vector in Rn and thinking of it as a column vector if you think of a column vector as being an n by 1 matrix, which of course you do. Okay, so let's make sure we understand how that works. So one often one thinks of elements of a vector space V as elements of the set of linear mappings from R into V. Okay, so this is kind of the opposite of what you do with dual space, right? With the dual space, you think of linear mappings from V into R. Here, we're thinking of linear mappings from R into V. And what is that linear mapping? If you take a vector v in V, what I want to do now is I want to define a linear mapping from R into V. And, you know, again, there's an obvious way to do this. Okay, and so, you know, if you just sort of take the pieces of information you have and try to define what I'm asking you to define, there's really only one way to do it. And it's like this. And I'm going to call this linear mapping L sub V. And so it's a linear mapping from R into V, and it's LV of, okay, so I'm going to take an element of R, which I'm going to call, let's say, A. Okay, so what's this going to be? So now this, I'm going to give you a little quiz on the principle of there's only one thing it can possibly be. So what's the only possible thing that I can put here? Apart from 0. That's a joke. Okay, so just take the data that I have on this side of the equation, right? And I want to assemble it. So what's the data that I have? I only have 2 pieces of data, V and A. And I want to take the pieces of data, V and A, and define an element of V. There's only really one way to do that. What is it?
A times V.
Thank you. Okay. Oops. Okay. So in this way, if you have a vector, the vector defines a linear map like so. And so in the case of Rn, okay, where V is equal to Rn, then this defines indeed a column vector, which is what you're used to, right? So if okay, so these are matrices now that are n by 1. Okay. So all right, so if you take a vector V in Rn, and we're going to assign to that the natural column vector. Okay, and so if I think of elements of Rn like so, okay, then the dual space, as we've already seen, okay, and so, you know, these are row vectors, and these are column vectors, and okay, so if I take an alpha, which is in the dual space, so let me write it as the dual space. And I take V as a vector in Rn, okay, and so I write alpha of V, okay, and so this is just the definition of what something in the dual does. It takes a vector and gives you a number, and what's that number going to be? It's simply going to be matrix multiplication of the row vector, okay, the 1 by n matrix alpha. Sorry. Let's see if I. Okay, so in the very concrete example of, you know, the very simple vector space Rn, we see that first of all, alpha elements of the dual are things that we understand well. They're just row vectors, or 1 by n matrices, and that the operation of an element of the dual space on an element of the vector space is just matrix multiplication. Okay. Now there's a caveat here. And this is where the potential confusion comes from, the your kind of familiarity with this example, and maybe you're overly familiar with this example. So you cannot make the identification of Rn by 1 with R1 by n. Okay, so if you take a vector in Rn by 1, which is going to be a column vector, this is not an operation that you should be thinking about doing. Okay, I mean, you can certainly write it down. I just did, but it has no meaning. And the reason is very simple, is that these two things represent things that are in intrinsically different spaces. This is in Rn, and this is in Rn dual. And Rn and Rn dual are not the same thing. Okay, they kind of have some similarities. They both are vector spaces of dimension n, but they are not the same. Okay, so don't be representing, vectors in Rn by 1 by n matrices, and don't be representing vectors in the dual of Rn by n by 1 matrices. Okay, because that's not valid. You're abusing the representations. Okay, and the reason you abuse those representations is very much related to the next thing that we're going to talk about, but in a super complicated way. So Again, so I'm going to introduce a topic which is in some way very familiar to you. You've worked with examples of these a lot in 212 and other courses as well. And we're going to be working with it in a super simple context. But I'm going to be, sort of digging a little bit more deeply into it and sort of really understanding what things are and what things are not. And the topic is bilinear maps. You may not have encountered the terminology bilinear map before, but you all know, and we'll see it come up, you all know of one example of a bilinear map, okay? Okay, but before we get to that, let's actually talk about what they are. And again, we're doing very simple linear algebra, no complicated infinite dimensional spaces or anything like that. Okay. So let V be a finite dimensional real vector space. Okay, a mapping. B. Now B, what it does is it takes a pair of vectors from V and gives you a number. Okay, and it's essentially, intuitively, it's linear in each of its two entries. Okay, so if you take an entry here and you fix it and just consider the second entry as being variable, then you just have a map from V into R. That map is linear. And then similarly for the other argument. Okay, so let me write that down. Okay, so what are these linear mappings to and from? So this is a linear mapping from V to R. Okay, and this also, of course, is a linear mapping from V into R. Okay, so in other words, these really are, I'm about to say that they're linear, and so therefore these mappings are actually elements of the dual space. Okay, so if these mappings are linear for each V0 and V. Okay, so again, the idea is very simple. I take V0 and I fix it. Okay, and then I consider the mapping which sends V to that. Okay, and that mapping is linear, and then similarly for the other entry. Okay, so that's what a bilinear mapping is. Okay, and so we're going to be talking, there's going to be an example that comes up for us of a very important bilinear mapping with physical meaning. Okay, but we got a bit of work to do before we get there. Okay, so we need to understand some of the basic properties of bilinear mappings. So denote by sigma 2 of V the set of bilinear mappings. Sorry, I apologize. I didn't mean that. That's a typo. I meant T0, 2, the set of bilinear mappings on V. Okay, so this seems like really weird notation. The 2 means this 2. The 0 means some other thing that it's part of some other bit of notation that is not going to be part of this class. Okay, so it's complicated notation because I'm specializing a more general kind of notation. Okay, so whenever you see this, it's just a set of bilinear mappings. Okay, so this is a vector space, first of all, and we're going to talk quite a lot about it, its dimension and stuff like that. And so to make it into a vector space, all I'm going to do is I'm going to tell you what the vector space operations are, addition and scalar multiplication, and then it's easy to verify that those satisfy the list of axioms for a vector space. Okay, so if I take two bilinear mappings, B1 and B2, okay, and I want to show you how to add them. And so, again, this is just the only rational way to combine symbols, all right? So this is going to be a bilinear mapping, and so I need to tell you what it does to two vectors, say V1 and V2. Okay, and what it does, okay, so this is the definition of B1 plus B2. Okay, and again, it's the only thing you can think about doing. Okay, and then similarly for scalar multiplication. Okay, okay, so here you're defining B1 plus B2, and here you're defining AB. And so B, B1, B2 are bilinear mappings. And A is a scalar. All right. All right, so you can sit down and verify that those satisfy the axioms of a vector space. Okay, so this then leads us into thinking about what's the dimension of this vector space. So we'll get around to that. Okay. So there's multiple kinds of attributes that you can give to bilinear mappings that are going to be important. One is symmetry. That's right. So symmetric. And that has the obvious meaning. Skew symmetric. And that has the obvious meaning. Okay. There's other attributes as well, which are combined with symmetric. So let me maybe do it like this. So if B is symmetric, then it is, okay. And so now for symmetric things, there's additional attributes you can talk about, which are definiteness attributes, okay? So positive definite means this, and this is probably terminology that you've seen before. So actually, sorry, let me do it this way. I apologize. I'm going to define positive semi-definite first. Sorry. Okay, so it's positive semi-definite if this is true. Okay, so if you give the same vector in both slots, you get something that's non-negative. Okay, and so B is positive definite. If it's positive semi-definite. And if B of V is equal to 0, implies that V must be equal to 0. Okay, certainly it's the case that if V is equal to 0, if V is equal to 0, then this is 0. And why is that? Well, that's just because of bilinearity requires that that map be linear. Okay, so if this is 0, if you give 0 into a linear map, you get 0. Okay. So positive definiteness. So this is always true, and positive definiteness means that. Okay. Okay. Oops. So this was the notation I tried to introduce before prematurely. Okay, so if the symmetric things we denote by sigma 2, sigma meaning symmetric. Okay. So here's a question that I'd like you to answer. Sorry, don't need symmetric there. When I talk about positive definite things, they're always symmetric. So what is a positive definite? Bilinear map. Okay, and so while the question maybe isn't perfectly clear, because the answer is that it's a positive definite bilinear map. Because we've defined all the terms there, it doesn't need any further explanation. But what I'm asking you is, this is a thing that you have encountered in your past life, and I'm asking you to tell me what that thing is. It is exactly some other thing that you've seen.
Is it a norm?
Getting there. So what's a common way to come up with a norm? Among all the norms, there's a special kind of norms that come from anybody?
A dot product.
We forbid in mathematics and engineering the use of the word dot product. Okay.
Yeah, it's an inner product.
Inner product, thank you. Dot product should be left in high school. And if you want to say, so let me have my little rant here because I get to do that since I'm the professor. Dot product means the standard Euclidean inner product, which means that you take two vectors in Rn and you multiply out their components squared and take the square root. Okay, that's the dot product. So I'm going to forbid you from using the word dot product, and for that thing I just described, that's called the standard inner product. Okay, so if you ever want to say dot product, pinch your tongue and say standard inner product, because that's what the dot product is. And the standard inner product is, of course, a special example of an inner product. Okay, and so a positive definite bilinear map is simply an inner product. It's exactly an inner product. So it's just synonymous with inner product. Okay, because if you look back at your linear algebra notes, okay, you will see that all of the properties of inner products, okay, so here's 2. Okay, inner products had that property, and inner products are symmetric, right? And they're positive definite. So they're positive semi-definite, and they also have this definiteness property. Okay, so so that's what I mean when I say that you've seen these kinds of things before. We're just going to talk about them a little bit differently. And one of the things that we're going to do, which is different from probably what you've seen before, is we're not just going to talk about inner products. We're actually going to talk about spaces, not necessarily spaces of inner products, although that's an interesting thing to talk about, but certainly spaces of symmetric bilinear maps. Okay. All right. Okay. So let's try to kind of organize ourselves to give us a little bit of direction here. So we started with a vector space V, and then from V we talked about its dual, and then we talked about bilinear maps. Okay, and so what did we do? We took a basis here, and it led to a basis here, which we called the dual basis. And we should be able to, therefore, okay, define a natural, if I give you a basis for V, there should be, just as there's a natural basis for V star, there should be a natural basis for the set of bilinear mappings on the vector space V. Okay, and so let's actually see what that basis is. And in doing so, we'll introduce like a little special bit of notation. Okay. The usual setup. Okay. All right. So we will define. Yeah, sorry. Okay, so when we did this construction of finding a dual basis for V star, what did we do? Well, I just gave you the dual basis. I defined it first. I said, here's, if I have a basis E sub j, then I have a way of constructing for each j an E super j. Right? And I told you what E super j was, and then we proved that it's a basis. Well, I'm going to do the same here. Same thing here. I'm going to say, I'm giving you a basis here, and then I'm going to define a bunch of vectors here, and then I'm going to show that they're a basis. And the basis is distinguished by having peculiar notation for it. Okay, so that's the notation. If I take a j and a k in 1 to n, then I define this this symbol. Okay, and we'll see that it has some attributes of a product as time goes by. But for now, let's just think of it as being a symbol that defines an element of the vector space of bilinear mappings. And the way that you pronounce this in English is you say that this is EJ tensor EK. That's the word that this means, is this stands for tensor. And so again, just like when I write T02, it seems unnecessarily bulky because I'm using a special case of more general notation. Well, the same thing is going on here. There's a special thing called a tensor product, and I'm looking at a very simple use of a tensor product here. And so that's why this thing is called tensor, okay, because it's like a tensor product. Okay. But none of that matters. The only thing that matters is that this is a symbol that defines a bilinear map. So I need to tell you what that bilinear map is. So I need to take EJ tensor EK, and well, it's a bilinear map. So what it does by definition is it takes two vectors and gives me a number. So I'm going to give it two vectors. Let's call them U and V. And it gives me a number. Well, of course, what I'm going to do is I'm going to write U and V as a linear combination of basis vectors. So I'm going to write U as U L E L, okay? And I'm going to write V as V M E M. Okay, and so again, as with all this stuff, we're using the summation convention, and I'm not allowed to use J or K here, okay, because those are free, right? They're free on this side of the equation, and they must remain free on this side of the equation. And so when I introduce U as a linear combination of the basis vectors, I have to use a summation index, and I used L here, which is not J or K. And then similarly, when I introduce an index for V, I can't use J, can't use K, can't use L. So I used M. Okay. All right. So what's the definition going to be? Okay, well, if you think about it for a second, so again, like so many things in what we're talking about right now, there's only one possibility here. So just like EJ, the dual basis vector EJ, pulls off the jth component of a vector, this is, and so that gives you a linear map. Well, here I'm going to have a bilinear map, so it's kind of quadratic, right? A product of linear things, and it's more or less obviously going to be that EJ picks out the jth component of this one, and EK picks out the kth component of this one and multiplies them together. Okay, that's the definition of EJ tensor EK. Okay, and so so notice that this thing is bilinear. Okay, so bilinear, kind of means a product of linear things. So it's linear in V and it's linear in U. All right. Okay, so then the obvious thing we're going to do okay, is I'm going to prove that this is a basis for the vector space of all bilinear maps. Okay. Now, how do you prove that? Well, you prove it the way you prove that things are a basis. You have to prove two things: linear independence and the spanning property. Okay, now in this case, when we did this for a V star, we were able by other means to know beforehand, without actually having a basis in our hands, the dimension of V star was the same as the dimension of V, well, at least in the finite dimensional case. Okay, and so in that case, we could get away with only showing one of linear independence and spanning, because if you have two vector spaces, or sorry, if you have a vector space and you know its dimension, and you produce a set of vectors with whose number is the same as the dimension, and either it's linearly independent or it spans, then it automatically has the other property. But in this case, we don't necessarily know a priori what the vector dimension of the vector space T02 of V is. So in this case, we really have to prove that it's both linearly independent and that it spans, unless we can sort of put together some other argument about what the dimension of the space of bilinear mappings is. Okay. So I've gone over a couple times, and this proof is definitely going to take more than 5 minutes. So we'll do this next time. I will stop the recording.